Let's learn how hierarchical data can be organized with trees. Right now on your machine, there's a root directory at the top. Inside it are folders, documents, downloads, pictures. Each of those folders can contain more folders, which contain even more folders, all the way down to individual files at the bottom. This nested organization is fundamental to how information is structured and easily retrievable. This isn't just a convenient metaphor, it's literally a tree data structure. Understanding trees means understanding the backbone of efficient data organization. To truly grasp its power, let's compare it to a simple, flat list of data, where every item is just stacked one after another. This approach often leads to an order of n search time, meaning the time taken grows linearly with the number of items. Notice how quickly the tree structure allows us to pinpoint information. By making logical decisions at each branching point, we eliminate large chunks of data from our search space. In contrast, a flat list requires us to check each item sequentially, leading to significantly more steps and slower retrieval. Every tree has a root node at the very top. Nodes with children are called parent nodes, and those that contain children but aren't the root are internal nodes. The leaf nodes are at the very bottom, containing the actual data without any further branches. These terms help us precisely describe and work with tree structures. The principle of hierarchical data organization, as seen in trees, is incredibly powerful. It powers how databases, for instance, index millions of records in milliseconds. It also enables features like autocomplete, finding suggestions instantly as you type by traversing specialized tree structures known as tri-trees. And it's fundamental to how social networks organize billions of friend connections, structuring complex relationships into navigable hierarchies. These real-world applications demonstrate the versatility and efficiency that tree data structures bring to complex systems. Every time you navigate folders on your computer, you're traversing a tree. You perform these tree traversals daily, instinctively understanding the efficiency of moving through organized data. By the end of this video, you'll see why trees beat flat lists, how binary trees work intuitively, and when to use them in real systems. Let's start with the simplest useful tree, the binary tree. Binary means each node can have at most two children, a left child and a right child. Why this constraint? Because 2 branches per node make algorithms predictable and efficient. Imagine a single node. It's just a box holding some data. Now we add a left child and a right child below it. Each of those children can also have up to 2 children. We keep going, level by level, and the tree grows downward. The top node is called the root. Nodes in the middle are internal nodes. Nodes at the bottom, with no children, are leaves. The 2-child limit isn't arbitrary. It's a design choice that unlocks powerful search and traversal algorithms. A balanced binary tree, like the one on the left, ensures efficient operations because data access paths are short and consistent. In contrast, a skewed tree, where nodes mostly branch in one direction, can lead to much longer search times, making it less efficient. This structure is everywhere: file systems, decision trees, expression parsers. While real-world systems like file folders often allow many subfolders, binary trees simplify this to just 2 branches per node. This simplification is key for designing algorithms that are consistently efficient and predictable across many applications. Now let's add ordering to the tree. A binary search tree, or BST, has a special property. For every node, all values in the left subtree are smaller, and all values in the right subtree are larger. This is how the root node, 10, establishes the initial structure based on its value. This spatial sorting is the key insight for how these trees work. It means that, to find or place a value, you start at the root and compare. If the target is smaller, you go left. If it's larger, you go right. This principle guides both searching and insertion, providing a logical path through the data. Let's insert numbers one by one and watch the tree organize itself. We start by inserting 5. Since 5 is smaller than 10, it is placed to the left as a child node. Next we insert 15. 15 is larger than 10, so it correctly goes to the right of the root node, 10. When we insert 3, it's smaller than 10, leading us left. But then, comparing it to 5, it's also smaller, so it continues its path to the left of 5. This demonstrates traversing multiple levels. Similarly, for 7, we go left from 10. But at 5, 7 is larger, so it branches to the right. This process of comparison and branching allows the tree to build itself based entirely on these ordering rules. Now that we have a tree, let's see how efficiently we can search for a particular value, like 12. This process leverages the same comparison logic we used for insertion. We start our search at the root 10. Is 12 larger or smaller than 10? It's larger, so the rule dictates we move to the right child. At 15, 12 is smaller, so we go left, and there we find 12. This search took only 2 comparisons to locate the value, illustrating the efficiency of a BST in finding data quickly. This is considered logarithmic time, complexity, or O of log n. But here's a critical trade-off that impacts performance. The efficiency of a BST heavily depends on its structure. A balanced tree, like the one we just built, keeps operations fast. But what happens if the tree becomes skewed and uses its balanced shape? If we search for 5 in a skewed tree, we have to traverse through every single node from the root all the way down, just like a linked list. This degrades search performance to linear time, or OON, effectively losing the primary advantage of the BST. This is why balance truly matters for optimal performance. What causes a tree to become skewed? Often, it's the order of insertions. If you insert numbers in an already sorted sequence, like 1, 2, 3, 4, 5, the tree will naturally form this problematic skewed chain. Each new number is always larger, forcing the tree to grow only to the right. This concept of ordered branching isn't just theoretical. Many real-world systems use similar logic to efficiently manage and retrieve data. Consider a file system, where files and folders are organized hierarchically. When you search for a file, like music, the system navigates through folders by comparing names alphabetically, just like a binary search tree. This hierarchical organization ensures that even with thousands of files, you can locate what you need quickly and efficiently. To overcome the skewed tree problem, advanced binary search trees exist, known as self-balancing trees, like AVL or red-black trees. These automatically adjust their structure after insertions or deletions to maintain that crucial O of log n performance, ensuring efficiency regardless of the order of data input. This progression highlights how understanding data structures like binary search trees and recognizing their potential pitfalls and advanced solutions is essential for building efficient and robust software systems in your professional career. Let's see a binary search tree in action. Imagine you're building an autocomplete system. You have a dictionary of words stored in a binary search tree, organized alphabetically. Let's visualize this. Here, we start with a binary search tree of words: apple, banana, mango, maple, and orange. The tree organizes them alphabetically, where words earlier in the alphabet are on the left and later words are on the right. Now the user types the letter M. When a user types a prefix like M, the system doesn't scan every word. Instead, it leverages the tree structure to jump straight to the subtree where all words starting with M are clustered. The system compares at the root, banana, determines that M comes after B, eliminates the left subtree, and zooms into the right subtree where mango and maple live. When the user types A, forming MA, the system further narrows the search. It compares MA with mango, confirming a prefix match and then refines the results to only include words that start with MA. This process quickly isolates mango and maple. The binary search tree structure groups related prefixes together spatially, so retrieval is instant. The system quickly returns mango and maple as suggestions. This is why autocomplete feels instant. Binary search trees organize data so that related items are neighbors, enabling fast filtered retrieval, not just exact matches. Many systems use similar principles for organizing and searching data. For example, when searching your file system for a folder like projects under work, the search path is narrowed down by prefix. Starting from the root, it navigates through documents and work to find projects, effectively eliminating irrelevant branches like downloads and desktop. Consider the performance implications. A flat list search, which sequentially checks every item, has a time complexity of O of n. This means the search time grows linearly with the number of items, making it slow for large datasets. In contrast, a binary search tree search leverages its organized structure to quickly narrow down options. It achieves a time complexity of O of log n, meaning search time grows much slower as the dataset increases, providing instant results. The performance difference is stark. Ultimately, binary search trees organize data spatially. Related items are neighbors, enabling fast-range queries and efficient filtering. This fundamental property makes them powerful for a wide array of applications, enhancing employability by improving understanding of efficient data structures. Trees are everywhere in production systems. Databases use B-trees to index billions of records. Every SQL query you run relies on tree-based indexing to return results in milliseconds instead of minutes. This logarithmic search property, denoted as O of log n, is critical for performance. It means that even as datasets grow exponentially, the time it takes to find a record only increases incrementally, ensuring rapid access to information in massive databases. Search engines use tritrees to organize strings hierarchically, enabling instant autocomplete and prefix matching across billions of documents. Every operating system uses tree structures to organize files. Without trees, finding a file would require scanning millions of entries sequentially. Social networks use tree-based traversal algorithms to find friend-of-friend connections and suggest new connections efficiently. The file system you navigate every day is just the beginning. Trees scale from your local machine to global infrastructure. They're the backbone of efficient data organization because they turn linear problems into logarithmic ones. When you need to search data frequently, maintain sorted order, or organize hierarchical information, trees are the answer. This framework helps you identify the optimal tree structure for your specific needs, guiding you from problem to solution. And this is just the foundation. Self-balancing trees, heaps, and graph traversal algorithms build on these principles. Trees are not abstract. They're the reason your software is fast,